Grade 12 Physics, Light Note Number 1, Review of Light and Review of Waves. This note will be a review from some of the wave content that you would have learned in grade 11. We're going to review some of the terminology and the types of waves or types of vibrations that make up waves. The first one we're going to look at is a transverse wave. The basis of a transverse wave is we have a vibration that is perpendicular to the rest axis. So we might have positive displacements, negative displacements. The positive ones are called crests, the negative ones are called troughs. And we can show that it has a wavelength. That would be the length from crest to crest. An example of a transverse wave might be a water wave. The next one is going to be a longitudinal wave, and this is going to be shown here on a spring. If we can send a vibration that's parallel to the rest axis, that'll be shown here by these compressions on the spring. The bunched up areas will be called compressions, and the stretched out areas have a special name. They're called rarefactions. So this here would be an example of something like a sound wave. The third type of wave that we would review is a torsional wave, and that's where we have some sort of twisting around the rest axis. So here we're just going to draw a spring where we might have some twisting going on. This would be something like a swing as you were a kid that you would twist around on. Another property of wave is wave interference. So the two types of interference we're going to look at are constructive interference and destructive interference. The first one here, we'll look at two waves that interfere constructively before and after. So let's say we have wave A with some positive amplitude on a collision course here with wave B. When they meet, we're going to constructively interfere. We're going to get a larger wave. In fact, the height of this larger wave when they interfere would be the height of A plus the height of B. As they continue on, they pass through one another. B will continue on to the left, A will continue on to the right at their original amplitudes. If we look at destructive interference, here let's say we're going to look at what happens before and after again. We're going to have a positive A on a collision course here with a negative trough, which is going to be B. When they interfere, again, we're going to add the amplitudes together, but if they have the same values, let's say positive 3 and negative 3, they're going to cancel out to form a node. Afterwards, they pass right through each other again. B continues on, and so does A. There's some key terminology we need to consider whenever we talk about waves, and we're going to look at what this terminology means on a transverse wave and a longitudinal wave. First, we're going to look at the amplitude. So an amplitude is just the displacement of a wave from the rest axis. So this is shown on each of them with the red arrows. The next thing that we're going to consider here, we're going to define a cycle. A cycle is just one crest and one trough, or one complete revolution of a wave. Here, we've defined a cycle. There includes a trough and a crest. And it's the same here on a longitudinal wave. We have a rarefaction with two half compressions within that cycle. If we have our cycles, we can now define a wavelength. A wavelength is just strictly the length taken for that cycle. So if we get out a ruler and measure that, we can measure our lambda. The next term here is going to be frequency. Frequency is the number of cycles that pass every second. So if you were sitting near the shore and you watched the waves go by, the number of waves that went past every second, that would be your frequency. Frequency is related to this next term, which is period. Period is just the time taken for a wave to do one cycle. So the time taken for a transverse wave to go up and down, or the time taken for longitudinal to vibrate left and right. It has a relationship with frequency. It's the inverse of that frequency. Finally, the velocity of a wave. It's a speed the wave it travels. It is the property of the medium. You cannot make a wave go faster or slower. The only way you can change that is by changing the medium that the wave travels through. Finally, all waves obey something called the universal wave equation. This equation works for any type of wave, transverse, longitudinal, torsional, or even electromagnetic wave. The equations listed there, the velocity equals the frequency times lambda, v is velocity in meters per second, frequency is in hertz, which is inverse second, and the wavelength is in meters. So let's quickly use that here in an example. Let's say we have some red light, so we're going to use an electromagnetic wave, and we're going to shine it on a table, let's say. The red light is going to have a frequency of 625 nanometers. Let's calculate the frequency of this red light. So we're going to list the wavelength here, 625 nanometers, and we have to remember nanometers 10 to the negative 9 meters. It is light, so we know its velocity. It's the speed of light, 3 times 10 to the 8. So let's calculate the frequency using the equation. We get a final answer here of 4.8 times 10 to the 14 hertz.